Pick something up off the ground right now. Go on. In your imagination, just reach down and grab something, a pencil, a stone, a little ball. Now hold it in the air and let go. It falls. Of course it falls. Gravity is so obvious, so constant, so absolutely taken for granted that the very act of letting an object fall feels like the universe saying, yes, exactly, that's right, that's how things are supposed to work. What if I told you that sound? Sound, the invisible ripple you make when you talk, when you clap your hands, when you hum a tune under your breath. What if I told you that sound can reach out and grab that object and hold it in midair against gravity? Not metaphorically, not with magnets hidden in the table, not with tricks, with sound, with the same kind of thing that's happening right now as my voice travels across this room and arrives at your ears. You are already shaking your head. I can see it. Some of you are leaning back, arms crossed, thinking, Feynman is about to do that thing where he makes us feel dumb. I'm not, I promise. Because here's the secret. You already know everything you need to know to understand this. You've known it since you were a child. You've felt it in your body. You've heard it in concert halls and thunderstorms and the backseat of a car with the bass turned all the way up. The physics is already in you. We just have to find it and follow it to the end. So let's start at the beginning. What is sound? Now be careful. This seems like a trivially simple question, and the answer most people give is actually not wrong. It's just incomplete in a way that will cost us everything later. People say sound is vibration. That's true. People say sound is a wave. Also true. But here's what I want you to hold on to. Sound is a wave of pressure. It is a traveling pattern of regions where the air is squeezed together, compressed, and regions where the air is pulled apart, rarefied. These compressions and rarefactions move through space at roughly 340 meters per second in air at room temperature, and when they arrive at your eardrum moves in and out, your brain interprets it, and you hear something. That's the whole mechanism. When sound travels through air, it's carrying energy. This is not a subtle point. It's not a bookkeeping abstraction. It's physical, real energy, and we can feel it. If you stand near a very loud speaker, you feel something pressing on your skin. Not the wind. There's no wind from a speaker. It's the sound itself pushing on you. At a rock concert, people in the front sometimes describe the feeling of the bass physically hitting their chest. This is real. The sound waves are physically transferring momentum to you. Your body is absorbing some of the energy of the sound. Here's where it gets interesting. When a sound wave hits an object, really hits it, interacts with it, the wave can exert a force on that object. It's a small force usually. Under ordinary circumstances, this acoustic radiation pressure, as it's called, is tiny compared to gravity. You don't have to worry about a conversation levitating your coffee cup. But what if we could make the forces add up? What if we could arrange the sound in a very clever way so that instead of just hitting the object and pushing it in one direction, the sound wraps around the object from all sides, and the forces, instead of canceling each other randomly, cooperate to push the object somewhere specific and hold it there? That is precisely the trick. And the key to the trick is something called a standing wave. Let me tell you about standing waves because they are one of the most beautiful things in all of physics, and they are hiding everywhere. You have probably seen a standing wave without knowing it had a name. If you take a piece of string and attach one end to a wall and shake the other end at just the right frequency, you can get the string to vibrate in a pattern that looks, and this is the amazing part, perfectly still. Parts of the string go up and down wildly, and other parts of the string barely move at all. The parts that don't move are called nodes. The parts that move the most are called antinodes. The whole thing is a wave, but it's a wave that has stopped traveling. Instead of moving through space, it's oscillating in place. It has a fixed skeleton, fixed geography, a frozen architecture of ups and downs. Now, why does this happen? Because when a wave travels forward and hits a reflective boundary, a wall, a rigid surface, it bounces back. Now you have two waves, the original wave going forward and the reflected wave going backward. If the geometry is right, if the distance between your source and your reflector is exactly the right multiple of the wavelength, these two waves interfere with each other in a very precise way. They add up in some places, amplifying each other to great intensity. And they cancel each other out in other places, leaving those spots almost perfectly still. The nodes are the places of cancellation. The antinodes are the places of maximum intensity. You've heard this your whole life. When you blow across the top of a bottle, the air inside resonates into a standing wave and you hear a pure tone. When an orchestra plays in a concert hall, the room itself forms standing waves at certain frequencies. Singers who know their craft can find the resonant frequencies of their chest cavities and project sound with incredible power by exciting standing waves in their own bodies. Standing waves are everywhere. They're the reason some notes in a pipe organ sound richer than others, the reason certain rooms have spots where speech is unnaturally clear and other spots where it sounds muddy. Now here is where we pull the rabbit out. In a standing wave, the pressure is not the same everywhere. At the nodes, the places where the wave appears not to move, the pressure oscillates most violently back and forth from high to low and back again, extremely rapidly. At the antinodes, the places of maximum displacement, doesn't mean the pressure actually stays closer to ambient. This is counterintuitive. The place that's wildly moving looks calm in terms of pressure. The place that looks perfectly still is actually the seat of the most violent pressure fluctuations. It takes a moment to sit with that, and it should. Don't rush past it. Now here's the trick that acoustic levitation exploits. When a small object sits in a standing wave, it experiences pressure from all sides. The pressure on any side of the object is not constant, it oscillates. But if the object is sitting near an antinode, where the pressure is oscillating like mad, those rapid oscillations don't average out to zero force on the object. They average out to a net force that pushes the object away from the antinode and toward the node. This is called the acoustic radiation force, and it acts like an invisible spring, pushing the object from both sides toward the node, where it comes to rest in a kind of acoustic trap. Do you see what just happened? We took a pressure wave and something invisible, something we usually think of as just sound, and we turned it into a physical cage, a cage with no walls, no bars, no wires, a cage made of nothing but organized vibration. The object floats right there at the node, because every time gravity tries to pull it down, every time a stray air current tries to push it sideways, the acoustic force pushes back and restores it to its equilibrium position. Now let me be honest with you here, because Feynman being honest is what we came for. The mathematics of acoustic radiation force is genuinely not simple. It was worked out properly, in full rigor, by a physicist named Louis Gorkov in 1962, and the derivation involves time-averaged quantities in the acoustic field, the compressibility of the object compared to the surrounding medium, and a potential function that the object naturally seeks the minimum of. When I say the physics pushes the object to the node, the real statement is that the object minimizes its acoustic potential energy by moving to the node, much the same way a ball on a hill rolls to the valley, because that's where its gravitational potential energy is lowest. The acoustic standing wave creates a landscape of potential energy with valleys at the nodes, and the object rolls into one of those valleys and stays there. Gorkov was standing on shoulders, of course. Nobody in physics ever isn't. The systematic study of sound and resonance goes back much further. In 1866, a German physicist named August Kundt devised a beautiful demonstration tube. You can still make it today with a glass cylinder, a bit of cork dust, and a vibrating rod, in which the cork dust would arrange itself into little piles at the nodes of a standing wave inside the tube. It was a way of making the invisible visible. You could see the standing wave by watching where the dust collected. The nodes were the quiet places, the places where the dust was not blown around, where it could settle. Kundt wasn't levitating anything against gravity. The geometry wasn't right for that. But he was showing the same organizing principle at work. Particles seek the nodes. The standing wave is a sculptor of matter. Now, in the decades after Kundt, people began to wonder, what if you oriented your standing wave vertically? What if you put your source below and your reflector above, or your two sources facing each other, and created a standing wave that ran up and down? Then the nodes would be at certain heights, and if the acoustic force pushing the object toward the node is stronger than gravity pulling it down, the object floats. The first proper demonstrations of acoustic levitation in the modern sense started appearing in the second half of the 20th century, and by the 1970s and 1980s, serious researchers at places like Jet Propulsion Laboratory and NASA were genuinely interested in it. And why? Because gravity is inconvenient. Not philosophically, I mean practically, in the laboratory. If you want to study how a liquid drop behaves, how it forms, how it freezes, how it crystallizes, you need to look at it without contamination, without it sitting on a surface and being affected by that surface. The perfect experiment would study a completely free drop, touched by nothing. Magnetic levitation works for some materials. Electrostatic levitation works for charged things, but acoustic levitation works for almost anything. Drop of water, pellet of medicine, tiny fragment of biological material, grain of sand, because almost everything responds to pressure, and pressure is universal. NASA studied acoustic levitation in microgravity to understand how it might work as a general container-free processing technique. If you ever need to mix or process a material in space without putting it in a vessel, which could contaminate it or change its chemistry, acoustic levitation lets you hold it in nothing, process it with nothing touching it, and observe it in perfect isolation. That is a genuinely useful capability, and it came from following the physics of standing waves all the way to its conclusion. But here I want to stop and say something about the way science works, because I think it's important and people often get it wrong. Someone in the audience is now thinking, okay, so acoustic levitation was invented for a purpose, it was engineered, and that's partly true. But the deeper truth is that every piece of this was discovered by people following curiosity rather than utility. Kundt put cork dust in a tube because he wanted to see where the nodes were. He wasn't thinking about levitating anything. The people who worked out the mathematics of sound pressure and radiation force were not thinking about medicine. They were thinking about waves, about how waves push things, about whether Maxwell's equations for light, which predict a radiation pressure, have an acoustic analog. They were following the question where it led, not following the application where it was funded. This is the thing about physics that drives bureaucrats a little crazy and fills me with joy every time I think about it. You cannot plan the important discoveries. You cannot say, we will now spend 5 years discovering something that will revolutionize pharmaceutical manufacturing. You follow the waves, you follow the curiosity. The applications arrive like unexpected guests, and you welcome them in, and it turns out they've been living there the whole time, waiting to be found. Now let's go deeper, because I told you the object sits at a pressure node, and I told you the acoustic force is related to the radiation pressure, but I haven't told you why the acoustic force pushes toward the node rather than away from it. Now let me try to give you a physical feel for this, because the mathematics is exactly right, but a little cold, and I want you to feel it. Imagine a small object sitting in a standing wave. The standing wave is oscillating. The pressure near antinodes is going up and down at the frequency of the sound. When the pressure on one side of the object goes up, it's pushing the object one way. Half a cycle later, the pressure goes down, and now the object is being pushed the other way. These forces are oscillating rapidly back and forth. If everything were symmetric, they would cancel, and the net force would be zero. But they're not quite symmetric, and here's why. When the pressure goes up, the medium around the object gets slightly stiffer, slightly denser. The wave speed changes a tiny bit. The relationship between the object and the wave field is subtly different during the high pressure phase than during the low pressure phase. These tiny asymmetries don't cancel. They accumulate over many cycles into a small but steady net force, and the direction of that force depends on whether the object is more compressible than the surrounding medium or less compressible. For most solid objects in air, they are much less compressible. You can barely compress a grain of metal while you can compress air a great deal, and this results in a force that pushes the object toward regions of low pressure oscillation, which means toward the nodes. For bubbles, the situation reverses. A bubble is more compressible than the surrounding water. You can collapse a bubble relatively easily, and so in an acoustic standing wave in a liquid, bubbles are pushed toward the antinodes. They collect at the antinodes. Objects and their bubbles want to be in opposite places. I find that charming. The wave discriminates between things that are stiffer than their environment and things that are softer. Stiff things go to the quiet places. Soft things go to the loud places. The wave sorts matter by compliance. There's an analogy I want to try here. Imagine you're floating in a swimming pool and someone makes waves. The waves push and pull on you. If you are a rigid person, stiff, unbending, a person who has perhaps had too much calculus, the waves push you around, but there's a subtle drift toward the troughs, the quieter regions. If you're a very soft, compressible thing, like a foam float, you get pushed toward the crests, the violent regions. The analogy isn't perfect, and I'd have to wave my hands a bit to make it precise, but the intuition is there. Your relationship to the medium, how you compare to the stuff around you, determines where the wave wants to put you. Now let me tell you how remarkable modern acoustic levitators actually are. We are not talking about levitating a grain of sand, though we can do that. We are talking about levitating drops of liquid. We are talking about manipulating those drops without touching them, moving them from one node to another by changing the phase of the sound waves, making them merge with other drops, making them separate. We are talking about suspending live insects, small fish, even small pieces of ants and biological material, alive, unharmed, floating in air, and studying how they behave. We can watch a drop of water freeze in midair and see what the crystal structure looks like when it forms without a surface to nucleate on. We can watch chemical reactions happen in a floating bead of liquid that has never touched a vessel. One of the things that astonishes me, and I use that word carefully because I try not to be astonished by things that merely look impressive, is that acoustic levitation has revealed something about how water freezes that we couldn't see before. When water freezes on a surface, the surface matters. The crystallization pattern, the way ice nucleates, is influenced by what the water is sitting on. But levitated water, freezing in air with nothing touching it, can be supercooled to nearly minus 40 degrees Celsius before it finally gives up and freezes. And when it does freeze, the ice crystals form in patterns that have never been seen when the water freezes on a surface. The absence of contamination, the absence of contact, reveals a purity of process that contact always conceals. You can only see what water wants to do when you remove every constraint that isn't water itself. That strikes me as a metaphor for something. I'll let you work out what. Let me tell you about another wrinkle that people often miss, and it matters because it's subtle and beautiful. I've been talking about a standing wave between one source and one reflector, like sound bouncing off a wall and interfering with itself, but you can also create acoustic levitation with two speakers facing each other, no reflector needed. The sound from each speaker travels toward the other, and where the two waves meet, they interfere and create a standing wave between them. You can move the nodes by changing the relative phase of the two speakers. Advance one speaker slightly, and the whole pattern of nodes shifts. This gives you a kind of acoustic tweezers, where you can grab an object that's floating in a node and move it smoothly through space by sliding the node under it. You can sort objects, move them along a track, route them like packages on a conveyor belt, except the conveyor is invisible and is made entirely of sound. People have built tiny acoustic conveyor systems that can route microgram-scale objects through complex paths. Pharmaceutical companies are interested because they want to handle very small, very pure quantities of expensive compounds without contamination. The objects ride the nodes like surfers riding waves, except the surfer controls the wave. It is one of those technologies that looks like science fiction from the outside and looks like straightforward physics from the inside. Once you have followed the argument all the way through. The magic isn't in the hardware. The hardware is just speakers and amplifiers and some control electronics. The magic is in the waves and what they do when you arrange them with care. Now, I promised you a mystery. I never give a speech without a mystery, because a speech without a mystery is just an announcement. Let me tell you where the edges of our understanding actually are. The basic physics of acoustic levitation, the Gorkov theory, the radiation force, the node-seeking behavior, this part we understand. But when the objects get bigger, when they approach the scale of the wavelength or exceed it, the simple picture breaks down. The object starts to scatter the sound in complicated ways. It deforms the very wave field that's supposed to be trapping it, and the object can start to spin. Acoustic levitated objects are often observed rotating, sometimes quite rapidly, and the physics of why they spin at the rate they do in the direction they do is connected to the angular momentum carried by the sound wave, which is connected to something called acoustic vortices, which are sounds waves with a twisted wavefront, a helical phase structure, and these things carry orbital angular momentum in a way that is genuinely analogous to, and in some mathematical ways identical to, the orbital angular momentum of photons in structured laser beams. This is a real frontier. People are working on it right now. Acoustic vortices, acoustic tweezers, acoustic torques. These are areas where the theoretical picture and the experimental picture are still being reconciled. There are phenomena in acoustic levitation that are fully reproduced by experiment and only approximately explained by theory, and there are predictions from theory that haven't yet been cleanly confirmed. This is what makes it exciting to be a physicist. You know roughly what the map should look like, but the edges of the map are uncertain, and the uncertain edges are exactly where all the interesting things live. And there is a deeper question underneath all of this, one that has bothered me in a delightful way for years. We talk about acoustic radiation force as if sound is pushing matter. But what is sound really? Sound is organized motion of molecules. The air molecules in a sound wave are not all moving in the same direction. They are oscillating back and forth, compressing and expanding in a pattern. The force the sound exerts on an object is not something the wave carries like a bullet carries momentum. Time-averaged effect of billions of tiny molecular collisions happening in a very precisely orchestrated pattern. When we say the acoustic force pushes the object to the node, we are abstracting over an unimaginable number of molecular interactions and finding a clean, simple behavior that emerges from the chaos. This is what physicists mean when they say a quantity emerges. The acoustic force is emergent, the concept of a node is emergent, the levitation is emergent. None of it exists at the level of individual molecules. At the level of individual molecules, all you have is molecules bouncing off the surface of the object with slightly different frequencies and amplitudes in different places. But zoom out, average over time, average over the oscillation, and a completely new structure appears, a force, with a direction that holds things against gravity. The collective behavior of the molecules, organized by the sound wave, creates something that no individual molecule could create. I find this profoundly beautiful, and I find it faintly unsettling in the best possible way, because it means that the concepts we use to describe the world, force, field, wave, node, are not primary realities. They are stories we tell about the behavior of many molecules all at once. And these stories are extraordinarily useful and extraordinarily accurate, but they are not the bottom. There is always a deeper bottom, and then deeper still. And the question of where the real bottom is, Teadu sako that is one of the great open questions of physics, and I don't know the answer, and nobody does, and that's wonderful. Let me connect this to something bigger, because I always do. Acoustic levitation is not just about acoustic levitation. It is an instance of a general principle that runs through all of physics, that fields exert forces on matter, and that the forces a field exerts depend on the spatial structure of the field. Gravity is a field, and the gradient of gravitational potential is the gravitational force. Electromagnetism is a field, and charges in an electric field feel forces that push them along the field lines or across them depending on the geometry. A sound wave is a field, a pressure field, a velocity field, and the gradient of the acoustic potential energy pushes objects towards specific positions. The same mathematics that describes acoustic levitation describes optical trapping with laser tweezers. A tightly focused laser beam, because of the way light's electromagnetic field exerts radiation pressure on small particles, creates a three-dimensional trap that can hold individual living cells, individual viruses, individual molecules, and hold them against Brownian motion and thermal fluctuations. The physics is identical in structure. You have a wave, you have a field associated with the wave, you have the gradient of an energy in that field, and the gradient force traps the particle. Light tweezers, acoustic tweezers, they are the same idea at different wavelengths, different scales, different regimes. And once you see this principle, that waves can organize matter, that fields can hold things against other forces, that the geometry of a wave determines the geometry of where matter will concentrate, you start seeing it everywhere. In biology, the cytoskeleton of a living cell is full of organized mechanical waves that help transport cargo. In geophysics, seismic standing waves in the Earth's crust concentrate stress at specific locations, and this is related to where earthquakes are most likely to occur. In cosmology, acoustic waves in the early universe, sound waves in the hot plasma of the Big Bang, organized the distribution of matter in patterns that we can still see today, hundreds of millions of light years across, in the large-scale structure of galaxies. The universe, just after the Big Bang, was a place where sound waves were organizing matter. The nodes of those primordial sound waves are, in some sense, the seeds of the galaxies. The universe levitates its galaxies with sound. Not quite, but not entirely, not either. You see why I love physics. You start with, can sound levitate a small ball? And you follow the argument, and follow it, and you arrive at the structure of the universe itself. The same principle, stretched across 40 orders of magnitude of scale, from the microgram fragment floating in an ultrasonic trap in a laboratory to the filaments of galaxies arranged across cosmic distances by acoustic oscillations in the infinite universe. The principle is not weakened by the generality. It becomes more beautiful, more true. Let me tell you what I think when I stand in front of a working acoustic levitator, and I have, or at least I have imagined it so vividly that the distinction feels small, and I watch a water drop floating in nothing, held there by invisible sound. What I think is not, what a neat trick. What I think is, the universe is so much stranger than our intuitions prepare us for. We evolved to understand objects that fall when you drop them. Gravity was there from the beginning, constant, reliable, the great organizer of our physical experience. The idea that you could use organized pressure oscillations to overcome gravity by pushing from every direction at once is not something evolution prepared us to intuit. We had to figure it out. We had to use reason and mathematics and experiment to find it. And here is the thought I want to leave you with. Every time we find something like this, acoustic levitation, optical tweezers, magnetic trapping, anything where we use the geometry of a field to hold matter in a configuration it would never reach on its own, we are demonstrating something remarkable about the nature of reality and the nature of knowledge. The universe contains these possibilities. They have always been there. The pressure nodes existed before there was a laboratory to create them. The acoustic radiation force existed before there was a Gorkov to calculate it. The possibility of levitation by sound was embedded in the laws of physics before there was any life in the universe to discover it. We did not invent acoustic levitation. We found it. We followed the logic of waves and pressure and force until the logic pointed at something that was already there, waiting. And I want you to sit with that for a moment, because the world is full of things like this. The laws of physics contain possibilities that nobody has found yet. There are principles out there, geometric, dynamical, deeply embedded in the structure of reality. That will be discovered by some curious person following a question that seems useless and leads somewhere nobody expected. There are levitations of a kind we haven't imagined, using forces we haven't yet thought to combine, holding matter in configurations that would seem to us today like pure fantasy. The child who asks, "Why does that happen?" is not wasting time. The scientist who follows a question about cork dust in a glass tube is not being impractical. The curiosity that asks, could sound hold something up, is not frivolous. It is precisely the thread that, when followed, leads from Kundt's tube to NASA's microgravity laboratory, to pharmaceutical manufacturing, to the acoustic organization of the early universe. That water drop floating in midair, sustained by nothing but organized pressure, is not magic. It's better than magic. It's physics. And physics is the story the universe is always already telling about itself. We just have to be quiet enough to listen. We have to be curious enough to follow the sound where it leads. And then we have to ask, we must always ask, what else is floating out there in the dark, held up by forces we haven't yet learned to hear?